Okay, let's jump into example 1. So example 1 really is review for you guys because we've hit upon this many times. So I do apologize that it's blurry. This is the best I could do. We're going to say evaluate a quadratic function. What does that really look like? Well, notice how and we practiced this yesterday too with our DRQs, so that's pretty cool. Go me. So we have f of negative 2. Remember, that's your x. So just take your time. Substitute carefully. All x's get replaced with negative 2. And at this point, start thinking about order of operations. Okay. Now we're ready to do the multiplication step, which would be this step, 2 times 4, and, careful, negative 3 times negative 2 is positive 6, plus 1, and we just wrap it up with the 15, meaning f of negative 2 equals 15. So what does that really mean? Well, that tells us a little more. That tells us that this parabola has a point on it that is negative 2, 15. It's not the only point on the parabola. There are infinite points on the parabola, but we know that this point is a solution to this parabola, to this quadratic function. Okay, let's move on to example 2. Graphing a quadratic function. I can't stress this enough. We don't have our graphing calculators at home, but the bottom line is graphing is not a challenge for us. If we were to have our graphing calculators, we would take this, we would think of it as y equals x squared plus 1, and we would type that in. Really, we'd end up typing I can't remember now. Is there an f of x or is there a y? But either way, we know they're the same, so we'd have to go into that bar up top in the graphing option, and we'd type in x squared plus 1, and then we'd hit enter, and we would get a graph. Now, the interesting part of this graph is if you went to a Desmos, desmos.com, I think, they would give you a virtual or digital graphing calculator. You could type this in, and you would see that it doesn't hit at, it's not centered on the y-axis. So x plus 1, I'm pretty sure, was his graph that he used. And let's see if I can find it without taking too long. That's all right. I want you to try and look up Desmos.com and try to see what the graph would look like of x squared plus 1. It's just a tiny difference from what you might expect. So x squared would really be right on that origin. All right. It's not working for me. That's okay. You guys can do it. Look it up. Look it up. Okay. Okay, we can come back to it. So once we have this, remember, another idea that we talked about was to split that screen, right? And do the x inputs, pick your x's. With an x squared, it's really important that you pick some numbers like, let's say negative 2, darn it, negative 1, 0, 1, and 2. notice how I started with a number and I went, trying to think about from 0 up and down 1 in either direction, or up and down 1 and 2 in either direction. And so what we end up getting is when negative 2 is squared, we get 4 plus 1 is 5. And actually, that means that when 2 goes in, we also get 5. When negative 1 goes in, we get 1 plus 1, so that's 2. And we'll also get that when 1 goes in. And when 0 goes in, we just get 1. So at 0, 1, we would have right about here, that's the vertex point, and then we have negative 1, and actually 0, 1 would be here, silly. And then at 1, 2, we have here and here. So it's just a little bit above that origin. And then we have 2 and negative 2, so negative 2, 5 way up. Okay. Okay.
That's the law. New York State law. She got a real tattoo on her arm. Oh, really? Yeah. Oh, wow.
Okay, so we have a parabola. It's a little bit shifted off of the origin. And we need to find the range of the function. So the range is going to be our y is really, notice how it's going from 1 and then up. So we're going to say that this is inclusive of 1 and travels to positive infinity. Now remember, I know we talked about this with a couple people, can't include infinity. Another way to say it is that y is greater than or equal to 1, right? I saw Kurt write that in his notes. Now what's the domain? Well, remember, domain is the x values. Let's just write that up here. The range is the y values. Let's change the colors too. So we have domain is x, and let's see. The x's are going to run from way over here to way over here. So that means if this parabola had all the room in the world, it would widen out so far in either direction. And that means it would run from negative infinity all the way through to positive infinity. Okay? All right. Yeah, that's good. Let's move on to the next page. Okay, so example 3. Now in example 3, I'm just trying to point out that if we were to write the standard form of a quadratic equation, let's do that. I'm going to do it in gray. So I'm going to try and line up the y equals ax squared plus bx plus c. What do you notice about this function? Well, it's really missing the b and the c. It only has an x squared. It has an ax squared. So if we think about it, that means that the a is equal to 1 because it's invisible, and the x squared is x squared. So what does that tell us? Well, check it out. The bx, the linear part of it, the linear term, is a 0, right? So that'd be 0x. The c, or the constant, is 0. And look at where this parabola crosses the x-axis. Okay? And look at where it crosses the y-axis. So the c tells us where it crosses the y-axis. Let's take a look over here at this other one and just try to sketch these things. Again, let's line it up. So we've got y equals ax squared plus bx plus c. Well, where's my c? Now I see that my a is 3, my b is positive 5, and my c is negative 2. Take a look at where you see that negative 2. Right? This c is the same as the y-intercept. It's always going to tell us where this parabola crosses the y-axis. Okay, so that's a really interesting thing to notice. It's going to help you when you're just trying to spot check things. Okay? All right, let's keep going. Example 4. Now, this was just an activity that Kurt did trying to point out how to find the turning point. And the turning point is really the vertex point. Okay, it's the point where things change direction. So look at the x's. The x's just keep going up and up and up and up and up, right? They're going from -1 all the way up incrementally by one number. But look at the f of x, or the y. This is the range, right? Notice how the range is going 4, 9, 12, and then, whoa, what's this? 13, and then what happens again? Goes down again. So that's interesting as you scan the y. You notice that the 13 is the point where things changed, and that means the vertex point is 2, 13. Okay. I'm really sorry that this was so long, but try to get it down on all whatever paper you need to use, okay? I'll see you soon.